Welcome to the Queen's College Physics Department's online DC Circuits lab. Because we're not in the lab, we can't access our components, and we're going to use this simulation instead. It's called the Circuit Construction Kit, and it's supplied by the PhET website, which is a part of the University of Colorado. For this lab, we're going to follow the online manual, just as you normally would. The only difference is that in the online manual we ask you to measure the resistance of certain components, and here in the Google Doc that accompanies this we are actually giving you those resistances. Other than that, you follow the procedures in the online manual. My purpose here is just to introduce you to this site. So we're going to need a power source. Here, that's a battery. And we're going to need some resistors. Now, the first thing is that there are two visual modes here. One is pretty pictures, but if you click this button over here, you go to circuit diagrams. These are what you would see in a circuit diagram and will see in the online manual. And I find them a little less cluttered, so I prefer this. Now, a circuit requires a path for electrons to flow on, so we grab some wires. We hold it very close, it snaps into place, and we're good to go. And we see the little negative circles flowing around. Why are electrons always blue? Anyway, they flow around in a counterclockwise direction because my battery has a large line on this side and a small one on this. So this is the positive side of the battery. This is the negative side of the battery. I can change that. I can do this and flip the battery the other way, and you see the electrons move the other way. Unfortunately, we can't use electron flow exclusively. I'll show you why in a minute. What we do have to use is conventional current. Conventional current is used exclusively in electronics, and it's as if there was positive charge flowing. This is not the way the world works, but it is what we're stuck with, and I'll show you why in just a second. I find this a little busy too, so I just shut it off. Okay, over here we have labels. You can turn off the labels, but it just hides the names of the components, and that's not the kind of guessing game we want to play here, so you can leave it on. Values is useful. Values is the value of each component in your circuit. This is a 9-volt battery. Well, I want it to be a 6-volt battery. You'll see that that's what it's specified as in the online manual. So I'll use the little arrow here to bring it down to 6 volts. Click anywhere else and it retains that value. The first value of a resistor in the Google Doc is 47 ohms. And it's a little finicky to use the slider, but there you go, 47 ohms. Now, you don't see anything. If you peek, you'll see that you got a very small current. The speed that the arrows are moving or how big the current is. That's not very informative. We want to measure things. So we're going to need some test equipment. We're going to need a current meter and a voltmeter. I'm also going to add a switch just because I can. So now I want to build my circuit with the test equipment. I connect that there. Let me open that switch. And now I want to break this. So I click there, I get a pair of scissors, I do that, I move this one out of the way, and now I get to put these back. I'm also going to neaten it up, so should you, because you're going to take some screenshots for your lab report. And now I have a circuit up. No, I don't. I'm missing a wire now, so my path has to be reestablished. Now I have a path, and the current is now reading 0 amps, which means it's active, but because the switch is open, there is no current flowing. If I close the switch, it becomes 0 ohms, no resistance, and I immediately see a 0.13 amp current. Now we want to use Ohm's law here, so current alone isn't enough. What we want is a voltage as well. So if I bring the probes, tips of the probes, to the ends of a component, I immediately see the voltage across that component. This is good. If I use another one here, it's also reading 6 volts. This is the only other component here that uses a voltage. But you may be wondering, since the resistor is dissipating energy, shouldn't it be negative? And you can just switch the probes. And this will help you keep track of whether it's which direction it's going in. So the resistor here is removing 6 volts from the circuit. If I flip the battery polarity like that, the probe actually, because I didn't change the probes, it actually now reads positive 6 volts. But note carefully, the current meter did not display a negative sign in either polarity, which means that the current meters here cannot be used to tell the direction of current. I guess that's the only real value that this might have. I'm going to switch it back. And now I have something I understand. So what else is available here? Well, we have wire resistivity. Tiny and lots. Not very helpful. Well, let me put it up to lots. Now, wire has resistance. So I put my voltmeter across it. You've already noticed, should have noticed, that there's a difference in the current, and that's because there is now a voltage being dissipated across that piece of wire. Worse, the more wire, the more voltage. If I even just stretch this, it climbs dramatically. That makes it pretty tough to do circuits if you have to start measuring the traces in the wires. So we prefer resistivity to be tiny, in which case the voltage here is 0. Now it's not in reality 0, but it is negligible as compared to the resistance of the components. This is mentioned in the Google Doc, and that's something you should talk about in your report. We also have battery resistance. Battery resistance is a funny term. A battery is not a piece of wire. A battery is a tube packed with some kind of chemicals undergoing a reaction that deliver electrons. If you attach wires to either end of the battery, it'll establish a voltage along that path. For alkaline batteries, that's 1.5 volts, and there's no way to change that other than using up the battery. Even 9-volt batteries, if you open them up, you'll find 6 1.5 volt D cells, not D cells, quadruple A cells. So there's no way we can talk about resistance, but resistance is, there's an effective resistance to a battery. Let's say it that way. The effective resistance to a battery, if large, simply adds more resistance to the circuit. It's not such a bad thing. Happily, the effective resistance of batteries is usually small enough to be ignored. It is negligible. Now, in the lab report, you should mention what happens if you short a battery. What is a short? Well, if I have a battery and I want to put a switch here because I don't want to spoil it for you, and I connect one end of the battery to the other. Now, there is no circuit element here. This is 9 volts delivered over 0 resistance. So you do a little calculation using Ohm's law and tell me what the current should be. And you should build this circuit when you're doing your lab, close that switch, and take a screenshot so that we know what happens. And that's the story of battery resistance. You have to build two series circuits. A series circuit can be built simply by cutting this and adding another resistor. Looking a little weird here. Second resistance in the list is 69.5, I think. You'll look it up. Pretty finicky. Good thing the arrows are there. And now you have a dramatically different current, and you can measure, sorry, put that like that. You can measure the voltage across this one and the voltage across this one. Voltage is measured at whatever's in between the two probes. You can also measure both. And because the resistance here is negligible in the wires, you can move it here and get the same reading. That's all part of your lab. A parallel circuit is a little different. Let me break this and this. I'll put this up here, I'll move this here, connect this here. And there. Well, you know what? Let me get rid of this too. In fact, let me delete this wire. Connect this one. And now I can go here, and I can go here, and I can get a voltage for my parallel circuit. Parallel circuit simply means there is a junction. These are the way the circuit diagrams are in the lab, and all you have to do really is duplicate those circuit labs. But it might help you to see it this way. If I bring this to here, and another wire here, break this one here, and bring another wire here. I've added all wires here, but now you clearly see there's a junction. A junction is a place where current can go both ways. Let's turn it on, and you can see they're going faster in one loop than the other because the resistance is lower, but there is current moving into both. That's a junction. Any circuit with a junction is a parallel circuit or has a combination of parallel and series. And that's the last one you have to do. You have to do a combination circuit. In each case, you'll calculate your effective resistance using the nominal values, and you'll compare it to the measured resistance, just as it says in the online lab. And that's it. If you're done, you can, or want at any time to get back to scratch so you can clean the place up, just hit the reset button. And you should occasionally take screenshots of your circuits, and you can put them into your lab report, which of course is a single Word document with Excel tables or whatever you have that you want to show us. And that's it. Good luck with your lab.